Hello YouTube. Have you ever thought about what a number is? So here I have a couple of numbers, just regular numbers, and they're not very interesting. And I want to think of a different way of visualizing numbers. So here's what I've come up with. So in the normal numbers we have one type of number here represented by a red dot. And I want to look at what happens when you multiply a number by another number. So in this case we have a red number that we can multiply by another red number. So we can multiply a normal number by another normal number. And nothing really happens, you just get another normal number indicated by the fact that the arrow goes back to itself. So this is not very interesting, and some mathematicians came up with more interesting systems. For example, the complex numbers, which are like this: 1 plus 23, and then you have an I, or 55 minus 1i. So you have the normal number still, but you introduce another type of number called I. So normally it's called the real component and the imaginary component. Doesn't matter so much, just two types of numbers. And these new numbers, they satisfy the rules that are shown here. If I multiply a normal number by a normal number, I get a normal number. If I multiply a normal number by an imaginary number, I get an imaginary number. And if I multiply two imaginary numbers, I get a normal number, but with a minus sign. So we can draw it like this. Now we have two types of numbers, red and blue. And if I multiply a red number by a red number, I get a red number. If I multiply a blue number by a red number, I get a blue number again. And if I multiply either one with a blue number, I get the opposite color. But if I go from blue to red, I also get a minus sign. So this is a little bit more interesting than just the red number. And there is a nice way we can visualize this, and that's what I want to show today. So I use OpenGL to draw things on the screen. And I won't go into too much detail, there's a lot of code here, but I just follow a tutorial that I found, and I'll put a link in the description. And I haven't made too many changes, but as you can see, there's a lot of setup code, and here are my utilities file. There's even more setup code, but this is all in the tutorial, so there's no point in me talking about it. The one thing I have added is some extra utility functions here, which you may want to refer back to if you want to replicate this code. So I can create a shader, which is a program to run in the GPU from a file. So it just reads a file and then does some more setup. Again, I'll refer you back to the tutorial. And then you can also create a shader program, which is a Vertex Shader, a fragment shader. Again, if you don't know what it means, don't worry about it. Just two separate parts of the GPU computation, which are necessary. But it can read those from files and then return an object that represents that computation that you can then run. And the other thing I've done differently from the tutorial is that I draw a vertex per pixel, and then I color each vertex inside the shader, which we'll get to later. So this is what one thing I've done differently. And then you have to call the draw arrays function with GL points instead of the argument that's in the tutorial. But again, this doesn't make a lot of sense if you haven't read the tutorial, but this is just if you want to refer back to it. I also link the source code, my source code, in the description. So now we get to the interesting part, which is what is the calculation that's running on the GPU to visualize this diagram that we had. So here is the vertex shader, which is the first part of the calculation. And the vertex coordinates, they go from -1 to 1. And it's a little bit easier to work with coordinates that go from 0 to 1. So I just normalize them, I call it, so they go from 0 to 1. And then I scale them later, so that instead of going from 0 to 1, they go from some arbitrary range that that's better to work with graphically. And for the thing I want to visualize, it's these numbers. It's not so important. But then this one just scales it from 0 to 1 to whatever this is. So, but here is the meat of the code. And the first thing you do is set this GL position. It's so the shader knows where on the screen that the point should be drawn, and then I do some computations to get a color that I want to output. So first we get the coordinates of the point corresponding to this pixel by mapping the coordinates, and then we do this iterative loop here. And this is where I apply these rules that are shown in the diagram. So so I have two number values, the real and the imaginary, x and y, they are called here. And each loop of the iteration, I calculate a new x value, which is following the rules of the diagram, and I'm calculating the equation z squared plus c. And in this case, c is gotten from the pixel value, and the z value starts at 0. So iterate that again and again until the point is far away from the origin, or you have reached the max number of iterations. And then based on the iteration number, you color the pixel. And doing that, you get this picture. Now, you may have seen this before. It's called the Mandelbrot Set. It's also why I don't want to go too much in detail with the algorithm. You can read about it on Wikipedia. But this calculation has been running on the GPU, and you can think of it as a way to visualize this multiplicative system that we showed in the diagram. Now, there are also other ways to do it, and I just want to show how that looks. So now I have a new input value called C. You can see it's an input value because it's called uniform. That's an OpenGL thing. I don't really want to get into that now, but just think of it as an input value that's coming from the Rust code or the CPU code. And then I have a little bit of different mapping of the range that we see. And here are the changes in the Rust code in the CPU side, where you first of all I have a different shader, but then I have to supply this input value by calling get uniform location to find out where it is located inside the shader, and then set it down here, set the value at that location to this number. And I also do that inside the main loop down here. I set the value in each iteration, and I increment it a little bit. That way you get an animation, which we'll see in a little bit. And then the shader code is only slightly different. Now these C values that I add on, they are fixed. Before they were given by the pixel value, now they are just fixed for every pixel. And instead the start values are not 0, they are given by the pixel value. And then but other than that, it's the same equation, and I run it. And again, I output in color. And you can try to play around with how you select the color based on different kinds of things. But I didn't get any nice pictures, so I'm not showing that. And here is how it looks if you run this code. So you can see it's quite a different shape than before. And now, because I'm animating this C value, the offset value, you can see it's changing, and we can sort of see how this multiplicative system looks for different input values. And you can let it run forever, and it will keep changing. Probably it will get trivial at some point. So, but remember that this was a multiplicative system that you get if you just have two different types of numbers, and then these rules for multiplying. But you can imagine what happens if you add more types of numbers, which is the interesting thing. Now, some mathematicians show that if you want to have a nice number system in the sense that this equation down here holds, then the next one you need, and you also want to have a division, something called division algebra, then the next simplest thing you can do must have four types of numbers. And if you draw it using the same method we did for the real numbers and the convex numbers, then you get this drawing. It's called the quaternions, and you can also do the visualizations with that, but I won't get into that. I'm more interested in trying to invent a new number system. So that's what I've done. It looks like this. Now I just made three dots, and then I connected them in some ways. I tried to plot it, and then I saw that it was a little bit boring, so I adjusted some things. But this is what I ended up with. You can see it's a lot less symmetric than the quaternions. Everything is like looking pretty nice, but here it's lopsided and kind of weird looking. But you do get some interesting pictures. So here is the actual math. This is again inside the shader, but I just wrote out the multiplication, how that works. And basically, if I multiply my two numbers here, now I call the red number I call I, the blue number I call J, and the yellow I call K. If you multiply them together, just multiply it out, and then in the end you get this. And applying the same algorithm as before, but with this new rules for multiplication, you get this code. Again, not so important, it's the same otherwise. And then you get the following. So the grayscale might be a little bit off, but I think it's good enough that you can see that there are some really interesting structures, and it's kind of less symmetric than the complex numbers for either of the two ways we did it, which you might expect from the diagram. But I think it's still quite interesting. And this is just one number system that I came up with. You can invent anything you want. And you can consider more dimensions. So here I'm actually calculating 3 dimensions, just plotting two of them. But you could have 7 dimensions or whatever you would like. So that's the end of it. I hope you found it inspiring, and you try your own experiments with inventing a new number system and seeing what kind of pictures you can get out of that.